Okay, let's do section 3.3. I'll break this into two videos. I'm breaking this into two videos because this is the most important part, finding a z-score. We'll use that throughout the rest of the semester. So these z-scores, when we say standardized value, what we mean is instead of looking at every billion number of samples and working with each of those, we're just going to take them all to a standard score, which we're going to use as a z-score. So I'll just draw a quick picture here with the population. So in here, we would have the population mean, and then we could start going out by standard deviations. Well, for every population, these numbers would always be different. Instead, what we're going to do is we're going to standardize them. We're going to take everything and change them to these z-scores, where the z-score of the mean is 0, and then the z-score of a standard deviation is 1. And so we can talk about z-scores and how far a data point is from the mean in terms of standard deviations. If there is one here at 1.5, that's 1.5 standard deviations above the mean. So let's learn how to do it. We round them to 2 decimal places because if you look in your Triola formulas with positive and negative z-scores, we need 2 decimal places on that chart. Okay, number of standard deviations that a data value is above or below the mean. There's no units. And here, we talked about significant values being more than 2 standard deviations away from the mean. So a z-score will do that. If we have a data value where the z-score is negative 2.43, that's significant because it's outside our range of 2 standard deviations. So z-scores make this so much easier. Well, to find a z-score, we need a formula, which apparently I deleted the slide. Here's how we find z. Take your data value, subtract the mean, divide by the standard deviation. So this first one, we've got, there's our data value, 4,000. Subtract x bar, divide by the standard deviation. Let's practice calculator here. So our z-score here, rounded to 2 places, is 1.22. So 4,000 grams is 1.22 above, or 1.22 standard deviations above the mean. Let's do the second one. Notice we're talking about all 2 different samples, 2 things we're looking at 2 different data values, but we can compare them by how far away they are from the mean. So here's our x bar. We got 99 degrees, subtract 98.2, divide by 0.62. That's my x bar. I can see it's above the mean because it's going to be positive because of the numerator. In fact, it's 1.29 standard deviations above the mean. So this tells me Erase a bunch of stuff. That a 99-degree temperature is further away from the mean than a 4,000 gram baby because the Z-score is higher. Talked about this already. Both of those were sitting in here like 1.29, less than 2, something like negative 2.85. That's going to be significant because it's more negative than negative 2. Let's see if this is significantly low. Z-scores make this so much easier than looking at all the data. My X, my platelet value is 75. Here's X bar, that's the mean. Standard deviation, 64.2. I got negative 2.56, so yes, because negative 2.56 is less than negative 2. So it's outside our range of normal values. It's unusual or significant. If you watch the video from section 3.2 when I did the stem plot and I had a data set of quiz scores, I believe. So this was a video from 3.2. I believe I had an X bar of 40.9 with a standard deviation of 15.1. And it looked like 81 might be an outlier. Well, I can check that very easily now because all I have to do is find the Z-score for 81. Subtract the mean, divide by the standard deviation. .66 rounding to the hundredths place. 2.66 is greater than 2, so yes, significant. Let's check the score of 10. Remember, it didn't look like it was an outlier because it was kind of close to the main data, the pack of data, so to speak. Negative 2.05. Okay. That is less than 2. It's not much less than 2, but it means it is significant. So with this data, and I don't know if they do it in this section, what is the cutoff score? For unusual, or let's say significant, / significant values above the mean. I'm doing this because then I don't have to check each individual data point. Because what I want is for what score is Z equal to 2.0. So I'm looking for the X, where the Z is 2. Yeah, first thing I'm going to do is multiply. 2 times 15.1 is x subtract 40.9. Notice these are always the steps. Then I'm going to add the 40.9 and get my x. (71.1) equals x. So any score, say 73, that is above 71.1, is significant. So Z tells me a lot, that it's easy to use, so much easier than adding and subtracting the standard deviations. Okay, I'll finish here with percentiles because later on I'll do them with Z-scores. So I'm just going to introduce them. Basically what a percentile is. For instance, I don't know if you took the SAT. You may have got something that said, oh, okay, you're in the 88th percentile in math. Well, what that means is there are 88% of the people are below you, so you're in the top 12%. That's what a percentile is. So really all you have to do, you look at data, find the number of values less than that, divide by the number of values. So really what this is, this gives you a proportion because it's less than 1. Then you multiply by 100 to change it to a percentage and the percentile. So let's see. Let's find the percentile for the data speed of 11.8. 11 point is here. There's 20 below it. So there's 50. Change that to a percent. So that's the 40th percentile for that data speed. So it gives the relative standing next to all the other ones. If you took something like 71.3, that's way on the high end. So that's 49. So there's 48 below it. This is in the 96th percentile. Just did that. Just did that. 40% below, 60 above. Quartiles, that's where I'm going to stop because I'll do a whole nother video on this.